High resistance grounding, or HRG, is a method of grounding electrical systems that uses a resistor in the ground path. The goal is to limit the ground fault current to a relatively low level. Let's explore the pros and cons of using a high resistance grounding system. Firstly, one of the primary advantages of HRG is reduced fault currents. By adding resistance to the ground path, HRG limits the magnitude of fault currents that can flow during a ground fault. This reduced fault current helps protect equipment from damage due to high-energy electrical faults. Secondly, HRG can improve the continuity of service. In a solidly grounded system, a ground fault typically results in an immediate trip of the circuit breaker, shutting down the affected portion of the system. HRG, on the other hand, allows a small, controlled amount of ground fault current to flow, which may be sufficient to keep the system operational while the fault is located and repaired. This can be particularly important for critical loads that need to remain powered. Thirdly, simplified fault locating is another benefit. Because HRG limits the ground fault current, it can make it easier to locate the fault. The fault current is typically highest in the immediate vicinity of the fault, so by measuring the current in various parts of the system, technicians can often pinpoint the location of the fault. Fourthly, HRG reduces arc flash energy. Arc flash is a dangerous phenomenon that can occur during electrical faults, releasing a large amount of energy in the form of heat and light. By limiting fault currents, HRG reduces the amount of arc flash energy release, improving safety for workers. Fifthly, HRG can reduce voltage distortions. Nonlinear loads such as variable frequency drives and electronic power supplies can generate harmonic currents that cause voltage distortions in the electrical system. HRG can help suppress harmonic resonance and reduce these voltage distortions. Now let's consider the cons of high resistance grounding. Firstly, HRG can potentially cause nuisance tripping. The low ground fault current in an HRG system can sometimes be difficult for overcurrent protection devices to detect, which can lead to nuisance tripping, with the circuit breaker trips even though there is no real fault. Secondly, HRG can lead to higher arcing times. Because the fault current is limited in an HRG system, the arcing time during a ground fault can be longer than in a solidly grounded system. This longer arcing time can damage insulation and equipment. Thirdly, HRG can cause a voltage shift. In an HRG system, the neutral voltage can shift away from ground potential during a ground fault. This voltage shift can affect sensitive electronic equipment that is referenced to ground. Fourthly, the design complexity of HRG systems is a consideration. HRG systems require careful design and analysis to ensure proper operation and protection. Factors such as the grounding resistance, the system voltage, and the characteristics of the loads must be taken into account. Fifthly, HRG can lead to higher equipment costs. The resistors and monitoring equipment required for HRG can increase the overall cost of the electrical system. There are some additional considerations when evaluating whether to use HRG. System size is one. HRG is typically used in larger electrical systems where the ground fault current would be excessive in a solidly grounded system. In smaller systems, the benefits of HRG may not outweigh the costs. The choice of grounding resistance is critical. If the resistance is too high, it can compromise protection. If the resistance is too low, it can reduce the benefits of HRG. A comprehensive arc flash hazard analysis should be performed to assess the potential hazards and determine appropriate safety measures. This analysis should take into account the specific characteristics of the electrical system and the potential for arc flash events. Local codes and regulations may have specific requirements or restrictions on the use of HRG systems. It's important to check with the local authorities to ensure that the HRG system complies with all applicable requirements. To further elaborate on the advantages, let's dive deeper into the implications of reduced fault currents. In solidly grounded systems, ground faults can result in extremely high fault currents, often reaching thousands of amps. These high currents can cause significant damage to equipment, including conductors, transformers, and switchgear. By limiting the fault current, HRG significantly reduces the risk of such damage, extending the lifespan of the equipment and reducing maintenance costs. The improved continuity of service offered by HRG is particularly valuable in critical applications where downtime can have significant financial or operational consequences. For example, in hospitals, data centers, and manufacturing plants, even a brief interruption of power can be disruptive and costly. HRG allows these facilities to maintain power supply during ground faults, minimizing downtime and ensuring that critical processes can continue uninterrupted. The simplified fault locating offered by HRG can save time and money in troubleshooting electrical problems. In solidly grounded systems, the high fault currents can make it difficult to pinpoint the exact location of the fault. With HRG, the limited fault current provides a clearer signal, making it easier for technicians to trace the fault and make repairs quickly. The reduction in arc flash energy is a major safety benefit of HRG. Arc flash events can cause serious burns, injuries, and even fatalities. By limiting fault currents, HRG reduces the risk of arc flash and improves safety for workers who may be exposed to electrical hazards. The reduced voltage distortions that HRG provides can improve the performance and reliability of sensitive electronic equipment. Harmonic currents can cause a variety of problems, including overheating of transformers and conductors, malfunctioning of electronic devices, and interference with communication systems. By suppressing harmonic resonance, HRG helps to maintain a clean and stable power supply, ensuring that electronic equipment operates properly. On the other hand, the potential for nuisance tripping in HRG systems can be a concern, especially in systems with a large number of sensitive loads. It is important to carefully select and configure the overcurrent protection devices to minimize the risk of nuisance tripping while still providing adequate protection against ground faults. The higher arcing times associated with HRG can also be a drawback, as prolonged arcing can damage insulation and equipment. To mitigate this risk, it is important to use high-quality insulation materials and to implement proper arc flash protection measures. The voltage shift that can occur in HRG systems can also affect sensitive electronic equipment. It is important to ensure that all equipment is properly grounded and that the neutral voltage is maintained within acceptable limits. The design complexity of HRG systems requires careful attention to detail. It is important to work with qualified engineers and technicians who have experience in designing and implementing HRG systems. The higher equipment costs associated with HRG can be a barrier for some organizations. However, it is important to consider the long-term benefits of HRG, such as reduced equipment damage, improved continuity of service, and enhanced safety. These benefits can often outweigh the initial costs of the system. When considering the system size for HRG implementation, it is generally more beneficial in larger electrical systems where the potential ground fault current is significantly higher than in smaller systems. In smaller systems, the cost and complexity of HRG may not be justified. Selecting the appropriate grounding resistance is crucial for achieving the desired performance of the HRG system. The resistance value should be chosen to limit the ground fault current to a level that is low enough to protect equipment and personnel, but high enough to allow for selective tripping of overcurrent protection devices. A comprehensive arc flash hazard analysis is essential for ensuring the safety of workers who may be exposed to electrical hazards. The analysis should take into account the specific characteristics of the electrical system, the potential for arc flash events, and the appropriate safety measures. Local codes and regulations may impose specific requirements for HRG systems. It is important to consult with local authorities to ensure that the system complies with all applicable requirements. HRG systems are often used in industrial facilities, commercial buildings, and healthcare facilities where continuity of service and safety are critical. They are also commonly used in systems with a large number of nonlinear loads. To summarize, HRG offers several advantages, including reduced fault currents, improved continuity of service, simplified fault locating, reduced arc flash energy, and reduced voltage distortions. However, it also has some potential drawbacks, including nuisance tripping, higher arcing times, voltage shift, design complexity, and higher equipment costs. When evaluating whether to use HRG, it is important to carefully consider the specific requirements of the electrical system and the potential benefits and drawbacks of HRG. It is also important to work with qualified engineers and technicians who have experience in designing and implementing HRG systems. By carefully planning and implementing the HRG system, organizations can improve the safety and reliability of their electrical systems and reduce the risk of costly downtime. Additionally, it's worth noting that the effectiveness of HRG depends on proper installation and maintenance. Regular inspections and testing are crucial to ensure that the grounding resistor is functioning correctly and that all connections are secure. Furthermore, personnel working on our new HRG system should be properly trained on the specific safety procedures and precautions associated with this type of grounding. In some cases, differential protection schemes can be used in conjunction with HRG to provide even more sensitive and reliable ground fault protection. Differential protection works by comparing the current entering and leaving a protected zone, such as a transformer or a motor. If there is a difference between the incoming and outgoing current, it indicates a fault within the zone, and the protection system will trip the circuit breaker. This type of protection can be particularly useful in HRG systems, as it can detect low-level ground faults that may not be detected by traditional overcurrent protection devices. Another important consideration is the coordination of overcurrent protection devices in an HRG system. It is essential to ensure that the circuit breakers and fuses are properly coordinated to selectively trip and isolate the fault without disrupting the entire system. This requires a thorough understanding of the system's impedance and fault current characteristics. Finally, it's worth mentioning that HRG is not a one-size-fits-all solution. The suitability of HRG for a particular application depends on a variety of factors, including the size and complexity of the electrical system, the types of loads being served, and the specific safety requirements. In some cases, other grounding methods, such as solidly grounded or low-resistance grounded systems, may be more appropriate. Therefore, it's essential to conduct a thorough engineering study to determine the optimal grounding strategy for each application. This study should consider all relevant factors and weigh the benefits and drawbacks of each grounding method. The ultimate goal is to select a grounding system that provides the best possible combination of safety, reliability, and cost-effectiveness. Higher resistance grounding offers distinct advantages in systems needing enhanced safety and continuous operation. However, it is crucial to understand the intricacies of the design and implementation to ensure its effectiveness and avoid potential drawbacks. Through careful planning, appropriate equipment selection, and adherence to safety regulations, HRG can significantly improve the overall performance and reliability of electrical systems.